There's a world out there, a world that haunts astronomers' dreams. A world so tantalizingly similar to our own that when it was discovered in 2015, headlines screamed, "Earth's cousin found," and "A second home for humanity, Kepler-452b." The name doesn't exactly roll off the tongue, does it? But what it represents is both beautiful and heartbreaking. It's a planet orbiting in the habitable zone of a sun-like star, with a year only slightly longer than our own. It might have water, it might have clouds, it might even have life, and we will never, ever go there. Not in your lifetime, not in your children's lifetime, not in 1,000 generations. This isn't pessimism, it's physics. And today, I'm going to spend the next 2 hours explaining exactly why Kepler-452b represents one of the most profound frustrations in all of human exploration. A destination we can see, we can study, we can dream about, but we can never, ever reach. Before we dive deep into the crushing mathematics of interstellar travel, before we explore the engineering nightmares and the physical barriers that stand between us and this distant world, I want you to understand something important. This isn't a video about giving up. This isn't about crushing your dreams or telling you that humanity has no future among the stars. This is about honesty. This is about understanding the true scale of the universe we live in, the real limitations we face, and what it means to be a curious, ambitious, technologically advanced species trapped on a single pale blue dot in an incomprehensibly vast cosmos. We're going to talk about some heavy topics today. We're going to discuss the speed of light and why it's not just a speed limit, but an absolute cosmic barrier. We're going to calculate exactly how long it would take to reach Kepler-452b using every propulsion technology we have or can realistically imagine. We're going to explore the concept of generation ships, vessels that would need to function as self-contained worlds for thousands of years. We're going to discuss time dilation, the economic impossibility of interstellar travel, and the philosophical implications of living in a universe where we can see wonders we can never touch. And through it all, I'm going to be completely, brutally honest with you. No false hope. No, maybe someday, if we just believe hard enough. Just the cold, hard physics that governs our reality. But before we get there, let me paint you a picture of what we're actually talking about. Because Kepler-452b isn't just any random rock floating through space. It's special, hauntingly, achingly special. And that's what makes this so painful. In July 2015, NASA's Kepler Space Telescope made an announcement that sent ripples through the scientific community and captured the public imagination like few discoveries before it. They had found a planet, and not just any planet, a planet that seemed almost designed to torment us with possibility. The announcement came during a time when exoplanet discoveries were becoming almost routine. By 2015, we'd found thousands of planets orbiting other stars. Most were nothing like Earth, gas giants larger than Jupiter, orbiting closer to their stars than Mercury orbits our Sun, super-Earths with crushing gravity and toxic atmospheres, frozen worlds in the outer reaches of their solar systems, tidally locked planets with one face eternally scorched and the other eternally frozen. Finding planets was no longer the challenge. Finding planets like Earth, that was the Holy Grail. And Kepler-452b seemed to be exactly that. Let's break down what makes this world so incredibly similar to our own. Because the details matter, and each similarity makes the impossibility of reaching it that much more frustrating. First, the star. Kepler-452b orbits a star called Kepler-452. This star is classified as a G2V yellow dwarf, which might not mean much to you, but here's what's significant. Our Sun is a G2V yellow dwarf. It's the same type of star, not similar. The same classification. This means Kepler-452 has approximately the same temperature as our Sun, approximately the same luminosity, approximately the same spectral characteristics. If you could somehow teleport to a planet orbiting Kepler-452, the sunlight would look almost exactly the same as it does on Earth. The same warm, yellow-white color, the same quality of light that has illuminated every moment of human history. Artists painting on Kepler-452b would mix the same colors we do. Plants photosynthesizing there would have evolved under the same wavelengths of light that drove the evolution of plants on Earth. But here's where it gets truly eerie. Kepler-452 is about 1.5 billion years older than our Sun. It's roughly 6 billion years old, compared to our Sun's 4.6 billion. This means if this system has followed a similar evolutionary path to our own solar system, we might literally be looking at what Earth could become in its future. Think about that. When we look at Kepler-452b, we might be seeing Earth 1.5 billion years from now. Or we might be seeing what Earth was like 1.5 billion years ago. Depending on how the system evolved, it's a cosmic mirror, showing us either our past or our future. Now, let's talk about the planet's orbit, because this is where things get almost surreal in their similarity. Kepler-452b orbits its star once every 385 Earth days. Let me say that again, slowly. 385 days. Our Earth orbits the Sun in 365.25 days. The difference is 20 days. 20 days out of 365. That's about a 5% difference. When scientists first saw this data, there was a moment of stunned silence. This wasn't some loose approximation. This wasn't a planet with a 6-month year or a 2-year orbit that we could kind of squint at and say, close enough. This was a planet with seasons that would feel almost familiar to us. Imagine living on Kepler-452b. Spring would arrive at roughly the same time. Summer would last roughly the same length. The agricultural cycles, if anyone is farming there, would follow a rhythm that human farmers would instinctively understand. School years would be about the same length. Pregnancies would take up roughly the same fraction of a year. Birthday celebrations would come around at roughly the same frequency. This might seem like a trivial detail, but it's not. The length of a planet's year affects everything about how life on that planet would experience time. A planet with a 10-day year would be a completely alien environment, with seasons flashing by in days. A planet with a 10-year orbit would experience decades-long seasons, with organisms potentially living their entire lives in permanent summer or winter. But Kepler-452b has a year that's only 5% longer than ours. It's uncanny. The planet sits at a distance of about 1.05 AU from its star. An astronomical unit, or AU, is the distance from Earth to the Sun, about 150 million kilometers. So Kepler-452b is 5% farther from its star than we are from ours. This places it squarely in what we call the habitable zone, or the Goldilocks zone, the region around a star where temperatures are just right for liquid water to exist on a planet's surface. Not too hot, not too cold, just right. Liquid water is the key ingredient for life as we understand it. Every living thing on Earth, from bacteria to blue whales, requires liquid water. Our cells are mostly water. Our biochemistry happens in water. Water's unique properties, its ability to dissolve substances, its expansion when it freezes, its high heat capacity, make it ideal for supporting complex chemistry and life. If Kepler-452b has liquid water on its surface, if it has oceans and lakes and rivers, then it has the fundamental requirement for life. Not a guarantee of life, but the requirement, the possibility. Now, we need to talk about the planet's size, because this is where things get a bit more uncertain, but still fascinating. Kepler-452b is estimated to be about 60% larger in diameter than Earth. We can't directly measure the planet's size with perfect precision because we detect it through the transit method, watching how much starlight it blocks as it passes in front of its star. Based on those measurements and some assumptions about the planet's composition, scientists estimate it's about 1.6 times Earth's diameter. If the planet is rocky, like Earth, this would make it what astronomers call a super-Earth. Not a gas giant, not a small rocky world like Mars or Mercury, but a larger version of Earth. Based on its size and likely composition, the planet's mass is estimated to be about 5 times Earth's mass. Now here's where the physics gets interesting. Mass and size determine surface gravity. If you could stand on the surface of Kepler-452b, assuming it has a solid surface, you'd weigh roughly twice what you weigh on Earth. So if you're 70 kilograms on Earth, you'd be about 140 kilograms on Kepler-452b. That's heavy. You'd definitely feel it. Walking would be more tiring. Running would be harder. You'd build up more muscle over time to compensate, but you'd always feel the extra weight pulling you down. But here's the thing. It's not impossibly heavy. You wouldn't be crushed. You could function. Astronauts train in environments with increased G-forces. Fighter pilots regularly experience much higher accelerations. The human body can adapt to 2G. It would just take time and effort. So if there's intelligent life on Kepler-452b, they'd be stronger than us, more robust, built for a heavier world. But they could potentially visit Earth and function here, just as we could theoretically visit their world and adapt, given time. The planet receives about 10% more energy from its star than Earth receives from the Sun. This is because while it's slightly farther from its star, the star itself is slightly more luminous than our Sun, due to its age. The net result is that Kepler-452b gets a bit more warmth than we do. This means the climate could be warmer than Earth's. Not scorching hot. Not a runaway greenhouse like Venus. Just warmer. Think of an Earth where the average temperature is maybe 5 to 10 degrees Celsius higher than our current average. More tropical. More humid. Maybe with larger polar ice caps melted, higher sea levels, different weather patterns. Or maybe not. Climate depends on so many factors beyond just stellar input. Atmospheric composition, cloud cover, ocean currents, continental configuration. All of these affect climate. Kepler-452b might be warmer than Earth, or it might have a thicker atmosphere that reflects more sunlight, keeping it cooler. We simply don't know. But the point is, it's in the right range. It's not a frozen ice ball. It's not a scorched desert. It's potentially habitable. And here's where the speculation becomes almost painful in its tantalizing possibilities. If Kepler-452b is a rocky planet, and if it has an atmosphere, and if it has water, then it's had 6 billion years for something to happen. 6 billion years. Earth is only 4.5 billion years old. In that time, life emerged within the first billion years. Single-celled organisms ruled for billions of years. Complex multicellular life emerged about 600 million years ago. Animals colonized land about 400 million years ago. Humans have been around for maybe 300,000 years. Civilization for only about 10,000 years. What could 6 billion years produce? If life emerged on Kepler-452b, at roughly the same time it emerged on Earth, relative to the planet's formation, then life there has had an extra 5 billion years to evolve. That's enormous. That's more time than it took for life on Earth to go from single-celled organisms to humans. Could there be oceans on Kepler-452b teeming with life more diverse than anything in Earth's oceans? Could there be continents covered in forests of alien plants, photosynthesizing under that yellow sun? Could there be animals, complex ecosystems, predators and prey, engaged in evolutionary arms races that have been running for billions of years? Could there be intelligence? Could there be cities? Could there be a civilization looking up at the night sky, seeing a faint yellow star 1,400 light-years away, wondering if anyone lives near that star? Could they have already detected our sun and catalogued it in their astronomical databases? Could they have given our solar system a designation in their language, something that translates to Sol System or Yellow Star 7392 or whatever naming convention they use? Could someone on Kepler-452b be having this exact same conversation right now, making a video about why they'll never visit Earth? These aren't science fiction questions. They're legitimate scientific possibilities based on what we know about the planet. We have no evidence of life on Kepler-452b. We've detected no artificial radio signals, no signs of industrial pollution in its atmosphere, no structures visible on its surface. But we also wouldn't necessarily expect to see such signs from 1,400 light-years away with our current technology. The James Webb Space Telescope, our most powerful space observatory, might be able to analyze Kepler-452b's atmosphere if we point it in that direction for long enough and get lucky with our observations. We could look for oxygen and methane in specific ratios that might indicate biological activity. We could look for industrial pollutants like CFCs that would be strong evidence of technological civilization. But even if we detect these things, even if we confirm that Kepler-452b has life, even if we somehow confirm that it has intelligent, technologically advanced life, we still can't go there. We can't meet them. We can't exchange information in any meaningful time frame. And that's what we're here to talk about. Because Kepler-452b represents the cruelest kind of temptation. A world that seems perfect for us. A world that might be teeming with wonders beyond our imagination. A world that we can detect and study and dream about. But a world we can never touch. All because of one simple, brutal fact. Kepler-452b is 1,400 light-years away. 1,400 light-years. You've heard numbers like this before, I'm sure. They get thrown around in documentaries and science articles. This star is 500 light-years away. That galaxy is 2 million light-years distant. The numbers are so big, they become abstract, meaningless. But I don't want this to be abstract. I want you to feel, in your bones, what 1,400 light-years actually means. So let's break it down in ways that will make the scale of this distance viscerally real. First, let's start with the basics. What is a light year? A light year is the distance that light travels in 1 year. Light is the fastest thing in the universe. It moves at exactly 299,792,458 meters per second in a vacuum. For simplicity, we usually round this to 300,000 kilometers per second, or about 186,000 miles per second. That's fast, incomprehensibly fast. In 1 second, light travels about 7.5 times around Earth's equator. In the time it takes you to blink, about 0.1 seconds. Light travels 30,000 kilometers, about 3/4 of the way around the Earth. When you look at the moon on a clear night, you're seeing it as it was 1.3 seconds ago, because that's how long it takes light to travel the 384,400 kilometers from the moon to your eyes. When we communicate with astronauts on the moon, there's a 2.6-second delay for round-trip communication. You say something, 1.3 seconds later they hear it, they respond. 1.3 seconds later, you hear their response. The sun is much farther away. Light takes about 8 minutes and 20 seconds to travel from the sun to Earth. This means when you look at the sun, you're seeing it as it was 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. We'd keep seeing sunlight, keep feeling its warmth for 8 minutes before darkness fell. Mars, at its closest approach to Earth, is about 3 light minutes away. At its farthest, it's about 22 light minutes away. When we send commands to rovers on Mars, we have to wait anywhere from 6 to 44 minutes for a round-trip communication. You send a command, drive forward 5 meters. At minimum, 6 minutes later, you get a confirmation. At maximum, 44 minutes later. This makes real-time control impossible. Everything has to be pre-programmed. Neptune, the farthest planet in our solar system, is about 4 light hours away. A radio signal takes 4 hours to get there, 4 hours to get back. 8 hours, round trip. Voyager 1, the most distant human-made object, launched in 1977, is currently about 23 light hours away, roughly 0.0026 light years distant. It's been traveling for over 47 years, and it's not even 3/1000ths of a single light year from Earth. At its current speed, about 17 kilometers per second, Voyager 1 is traveling at 0.0057%, the speed of light. Now, let's talk about actual light years. The nearest star system to our Sun, Alpha Centauri, is 4.37 light years away. That's about 41 trillion kilometers, or 25 trillion miles. Voyager 1, traveling at its current speed, would take about 73,000 years to reach Alpha Centauri if it were headed in that direction, which it's not. Alpha Centauri is our closest stellar neighbor. It's right next door, in cosmic terms, and it's 4.37 light years away, a distance that would take our fastest spacecraft 73,000 years to traverse. Now multiply that distance by 320. That's how much farther away Kepler-452b is compared to Alpha Centauri. Kepler-452b is 1,400 light-years distant. That's approximately 13.2 quadrillion kilometers. That's 13 quadrillion, 200 trillion kilometers. Let me put that in perspective with some comparisons that might make it more concrete. If you could drive a car to Kepler-452b at highway speeds, 100 kilometers per hour, driving continuously without stopping, it would take you 15 billion years. That's longer than the current age of the universe, which is 13.8 billion years. You would have had to start driving before the universe existed to get there by now. If you flew in a commercial airliner at cruising speed, about 900 kilometers per hour, the journey would take 1.67 billion years. You'd have to have started flying before complex multicellular life evolved on Earth. The Parker Solar Probe, currently the fastest human-made object when it's at its closest approach to the Sun, reaches speeds of about 163 kilometers per second. That's blistering fast, about 0.05% the speed of light. At that speed, it would take approximately 2.8 million years to reach Kepler-452b. Let's sit with that number for a moment. 2.8 million years. 3 million years ago, our ancestors were Australopithecus afarensis, the same species as Lucy, the famous fossil discovered in Ethiopia. They could walk upright and use simple stone tools, but they had brains about a third the size of modern humans. They couldn't speak in any language we'd recognize. They couldn't create art, build structures, or do mathematics. Everything that makes us human. Everything from language to agriculture to writing to science to spaceflight. All of it has happened in the last 10,000 years or so. Really, the last 3,000 years, for most of what we consider civilization. And we're talking about a journey that would take 280 times longer than that. If Australopithecus had built and launched a spacecraft using technology identical to our Parker Solar Probe 2.8 million years ago, that spacecraft would be arriving at Kepler-452b right about now. And the descendants of Australopithecus, us, modern humans, would be receiving the first data from a mission that started before we existed as a species. Can you imagine maintaining continuity of purpose for that long? Can you imagine caring about a mission that was started 2.8 million years ago? Can you imagine even remembering that such a mission existed? But wait. The Parker Solar Probe was using the sun's gravity to accelerate to those speeds. It can't maintain that velocity indefinitely. Voyager 1, which has actually left our solar system and is on an eternal journey into interstellar space, is a better baseline for a true interstellar mission using current technology. Voyager 1 is traveling at about 17 kilometers per second relative to the Sun. At Voyager's speed, it would take approximately 25 million years to reach Kepler-452b. 25 million years ago, the Earth was in the Miocene epoch. Antarctica was covered in ice, but it was still freezing over, gradually becoming the frozen continent we know today. The ancestors of modern apes, the creatures that would eventually give rise to gorillas, chimpanzees, and humans, were just beginning to emerge as distinct lineages. Grasses were spreading across the world's plains, creating vast savannas where there had once been forests. The ancestors of horses had 3 toes and were about the size of large dogs. Elephants existed, but mastodons and mammoths wouldn't evolve for millions of years yet. Humans, not even a glimmer of a possibility. Our lineage wouldn't split from the chimpanzee lineage for another 19 million years. That's how long a journey to Kepler-452b would take at the speeds we can actually achieve today. You could fit the entire evolutionary history from early apes to modern humans into that journey, with millions of years to spare. And here's the really painful part. We've been to the moon. We've sent rovers to Mars. We've landed on comets and asteroids. We've sent probes to explore the outer solar system. Space exploration feels achievable because we've achieved it. We've crossed these vast distances and done amazing things. But all of that, all of our space exploration to date, has taken place within our own solar system, within a region of space that spans maybe 12 light hours at the most. We've never sent anything outside that bubble. Voyager 1 and 2 are crossing the boundary, entering true interstellar space. But they're still within what we consider the sun's sphere of influence. Going to another star, even the nearest star, is a challenge thousands of times greater than anything we've done. And Kepler-452b isn't the nearest star. It's 320 times farther than the nearest star. If you plotted the solar system on a map where Earth's orbit was 1 meter in diameter, Alpha Centauri would be about 270 kilometers away. Kepler-452b would be 86,000 kilometers away. That's more than twice the circumference of Earth. In this scale, all of human space exploration, everything we've ever done, has taken place within about 30 meters of home. And we're talking about a journey of 86,000 kilometers. But distance alone doesn't fully capture the problem, because there's something even more fundamental standing in our way. The speed of light itself is a barrier we cannot cross. And that brings us to the real heart of why Kepler-452b is unreachable. Let's imagine, for a moment, that we solve every engineering problem. We develop perfect propulsion systems. We have unlimited energy. We have materials that can withstand any stress. We have life support that never fails. Money is no object. Political will is infinite. Everyone on Earth is united in the goal of reaching Kepler-452b, even in this fantasy scenario. Even with every practical problem solved, we still face an absolute, fundamental, unbreakable barrier: the laws of physics. According to Einstein's theory of special relativity, which has been tested countless times and confirmed with extraordinary precision, nothing with mass can reach or exceed the speed of light. Not, "It's really hard." Not, "We need better technology." Cannot. It is physically impossible. Let me explain why. Because this is crucial to understanding why Kepler-452b is forever out of reach. In classical physics, the physics we intuitively understand, speed is simple. If you're going 50 kilometers per hour and you accelerate by 50 kilometers per hour, you're now going 100 kilometers per hour. If you had infinite energy, you could keep accelerating forever, getting faster and faster without limit. But Einstein showed that the universe doesn't work that way. As you approach the speed of light, several strange things happen, and they all conspire to prevent you from ever reaching that ultimate speed. First, your mass increases. Not your rest mass, the mass you have when you're standing still, but your relativistic mass, the mass you effectively have due to your motion. As you go faster, you get heavier. And the faster you go, the more dramatic this effect becomes. At 10% the speed of light, your relativistic mass is only about 0.5% greater than your rest mass. Barely noticeable. But at 90% the speed of light, your relativistic mass is about 2.3 times your rest mass. At 99% the speed of light, it's about 7 times your rest mass. At 99.9% the speed of light, it's about 22 times your rest mass. And it gets worse. At 99.99% the speed of light, your mass is about 71 times your rest mass. At 99.999% the speed of light, it's about 224 times. The closer you get to light speed, the more massive you become, approaching infinite mass as you approach light speed. This means that as you go faster, you need more and more energy to accelerate further, because you're pushing more and more mass. At some point, you'd need infinite energy to make even the tiniest additional acceleration. You can never reach the speed of light, because doing so would require infinite energy, which doesn't exist. It's like trying to climb an infinitely steep mountain. You can get partway up, even pretty far up if you're strong enough, but the slope gets steeper and steeper, requiring more and more effort for each additional meter of altitude. Eventually, the slope becomes vertical, then beyond vertical, then infinite. You can't reach the top because there is no top. It's asymptotic. But, you might ask, what about light itself? Light travels at the speed of light. How does it manage? The key is in that phrase I used earlier. Nothing with mass. Light has no mass. Photons, the particles of light, are massless. That's why they can travel at the speed of light. In fact, they must travel at the speed of light. They can't go slower or faster. From the moment a photon is created, it's moving at exactly c, the speed of light, and it continues at that speed until it's absorbed. Anything with mass, like atoms, molecules, spacecraft, or human beings, cannot reach light speed. This isn't a technological limitation. This is fundamental to how space-time works. You could have technology 1 billion years more advanced than ours, with mastery over matter and energy that seems godlike to us, and you still couldn't break this rule. So, let's accept the speed of light as our absolute maximum. Let's imagine we somehow develop a propulsion system that can accelerate a spacecraft to a significant fraction of light speed. What would that journey look like? At 1% the speed of light, about 3,000 kilometers per second, the journey to Kepler-452b would take 140,000 years. That's longer than anatomically modern humans have existed. Homo sapiens emerged roughly 300,000 years ago. But behavioral modernity, the stuff that really makes us human, language, art, complex tools, only emerged about 50,000 to 70,000 years ago. The entire span of human civilization, from the first agricultural settlements to the present, is only about 12,000 years. A journey of 140,000 years is incomprehensible. You'd need not just a generation ship, but a civilization ship, maintaining technological knowledge, social structures, and sense of purpose across thousands of generations. At 10% the speed of light, a much more ambitious goal, the journey would take 14,000 years. This is still an absolutely enormous timescale. Written language has only existed for about 5,000 years. The entire historical record, everything we know about human civilization from written sources, could fit into this journey less than 3 times. Imagine launching a mission in the year 10,000 BCE, right when the last ice age was ending, and humans were just beginning to experiment with agriculture. That mission would be arriving at Kepler-452b right about now, in 2025 CE. And the people arriving would be the descendants, through 500 generations, of those original Ice Age humans. Would they remember Earth? Would they care? Would they even speak a language that the original mission planners could recognize? At 50% the speed of light, which would require absolutely staggering amounts of energy that we can barely even conceptualize. The journey would take 2,800 years. This is the span from ancient Greece to the present. When Plato was teaching at the Academy in Athens around 380 BCE, almost exactly 2,800 years ago, humans were using bronze and iron tools. The Roman Empire didn't exist yet. Christianity, Islam, Buddhism in its modern forms, all of these were in the future. The printing press, the scientific revolution, the industrial revolution, computers, spaceflight, all of it was unimaginably far in the future. If the ancient Greeks had launched a mission to Kepler-452b at 50% light speed, it would just now be arriving. And we, the recipients of that mission's data, live in a world that would be completely incomprehensible to them. We have technologies they couldn't even have words for. We understand the universe in ways that would seem like magic to them. Would a civilization that began in ancient Greece and evolved in isolation for 2,800 years have any cultural continuity with those original Greeks? Would they worship the same gods? Would they speak a descendant of ancient Greek? Or would their language have transformed beyond recognition? Would they even remember that they came from Earth? Or would Earth have become a myth, a creation story told by elders around the campfire? But there is a loophole, sort of. It's called time dilation, and it's one of the most mind-bending consequences of relativity. According to special relativity, time passes differently for objects moving at different speeds. The faster you go, the slower time passes for you relative to someone who's stationary. This isn't an illusion or a trick. Time literally passes at different rates. At everyday speeds, this effect is utterly negligible. Even at the speed of a fighter jet, The time dilation is measured in nanoseconds over a flight, but as you approach the speed of light, the effect becomes dramatic. At 50% the speed of light, time passes about 13% slower for you than for someone at rest. So while 2,800 years pass on Earth, you'd only experience about 2,425 years on the spacecraft. You save 375 years. Better than nothing, but still an incomprehensibly long journey. At 90% the speed of light, time dilation becomes much more significant. Time passes at about 44% the rate for you. A journey that takes 1,556 years from Earth's perspective would feel like about 680 years to the crew. You've cut the subjective journey time by more than half, but 680 years is still 25 to 30 generations. Still a multi-generational civilization ship. At 99% the speed of light, you're experiencing time at about 14% the rate of someone on Earth. The 1,414-year journey from Earth's perspective would feel like only about 200 years to the crew. Now we're talking about something that's at least conceivable as a multi-generational journey. Maybe 7 to 8 generations, if people live long lives. At 99.9% the speed of light, time dilation is dramatic. Time passes at about 4.5% the rate for you. The 1,402-year journey from Earth's perspective would feel like only 63 years to the crew. That's a single human lifetime. You could leave Earth as a young adult, travel through space, experiencing 63 years of life, and arrive at Kepler-452b in your old age. This seems like the solution. Accelerate to 99.9% light speed. Use time dilation to make the journey survivable. Arrive at your destination within a single lifetime. Problem solved, right? Not even close. Because accelerating to 99.9%, the speed of light requires absolutely mind-boggling amounts of energy, and it introduces a whole new set of terrifying problems. Let's talk about energy first. The kinetic energy of a moving object in relativity is given by a formula that approaches infinity as you approach light speed. To accelerate even a small spacecraft, say 1,000 tons, about the mass of 3 fully loaded 747 aircraft, to 99.9%. The speed of light would require roughly 21 joules of energy. To put that in perspective, that's about the total energy humanity currently consumes in an entire year. The entire global energy consumption. Every power plant, every car, every light bulb, everything, for a full year, just to accelerate 1,000 tons to 99.9% light speed. And that's just to speed up. To slow down when you arrive at Kepler-452b, you need the same amount of energy again. So double it. 2 years of global energy output, just for propulsion. For a tiny 1,000-ton spacecraft. But wait, a 1,000-ton spacecraft can't carry a meaningful payload for a decades-long journey. You need life support, radiation shielding, living quarters, food production facilities, backup systems, and actual humans. A realistic interstellar spacecraft would need to be much larger, probably tens of thousands of tons at minimum. Scale up to a 10,000-ton ship, and you need 10 times the energy. That's 20 years of global energy output. For a 100,000-ton ship, which is still relatively modest for an interstellar vessel with full life support, you're looking at 200 years of current global energy output. Where does that energy come from? Even if we could build fusion reactors with perfect efficiency, even if we could harness antimatter, which we can barely produce and store, the fuel alone would be massive. And massive fuel requires more energy to accelerate, which requires more fuel, which requires more energy. It's the tyranny of the rocket equation on a cosmic scale. There's another problem with traveling at 99.9% light speed. From Earth's perspective, 1,402 years still pass. You leave Earth, experience 63 years of travel, and arrive at Kepler-452b. But on Earth, 1,402 years have gone by. Everyone you knew is dead. Everyone they knew is dead. Dozens of generations have passed. The civilization you left might not even exist anymore. Nations rise and fall. Languages evolve beyond recognition. Technology transforms. You're not just a space traveler. You're a time traveler, jumping 1,400 years into the future. And there's no going back. If you tried to return to Earth, another 1,400 years would pass there. You'd arrive 2,800 years after you originally left. The Earth you knew would be as ancient to the people you meet as ancient Rome is to us. This is called the twin paradox. Although it's not really a paradox. If you have a twin who stays on Earth while you travel to Kepler-452b and back at near light speed, you might age 126 years, 63 years each way. But your twin would die millennia ago. Their great-great-great-grandchildren's great-great-great-grandchildren would be ancient history. And here's perhaps the cruelest twist. You can't even communicate. Radio signals travel at the speed of light. If you send a message back to Earth saying, "We've arrived safely," that message takes 1,400 years to get there. By the time Earth receives your message, 2,800 years have passed since you left. 1,400 years of travel plus 1,400 years for the signal. A round-trip communication would take 2,800 years. You ask Earth a question. Wait 1,400 years for them to receive it. They answer immediately. You wait another 1,400 years to receive their response. By the time you get an answer to, "How's Earth doing?" the Earth that sent that answer is 1,400 years in the past from your perspective. But from their perspective, they answered a question asked 1,400 years ago by people who are ancient history. You're not exploring space at these speeds. You're exploring time. And you can never go home. Not to the home you left. But let's set aside the philosophical and social implications for now. Let's focus on the pure engineering nightmare of traveling at 99.9% light speed. Because even if we solved the energy problem, even if we accepted the time dilation consequences, we'd face another absolutely devastating problem: space debris. Space is not empty. We like to think of it as a perfect vacuum, and compared to Earth's atmosphere, it essentially is. But it's not completely empty. There's dust. There are stray hydrogen atoms, maybe 1 per cubic centimeter on average in interstellar space. There are larger particles, microscopic grains of silicon and carbon from ancient supernova explosions. There are occasional larger chunks, rocks, and ice balls drifting through the void. At normal speeds, these things are a minor concern. The International Space Station occasionally has to dodge larger pieces of space junk in Earth orbit. Satellites are sometimes damaged by micrometeorite impacts. But we're talking about impacts at speeds of maybe 10 to 20 kilometers per second. Fast, but manageable. At 99.9% the speed of light, you're traveling at about 300,000 kilometers per second. Every atom, every dust grain, every particle becomes a devastating projectile. The kinetic energy of an impact is 1/2 mass times velocity squared. Velocity squared. That means when you double your speed, the impact energy quadruples. When you increase speed by a factor of 10, the impact energy increases by a factor of 100. At 99.9% light speed, a single grain of sand, massing perhaps 1 milligram, would hit your spacecraft with the kinetic energy of approximately 200 tons of TNT. That's roughly the yield of the bomb that destroyed Hiroshima. 1 grain of sand, a pebble the size of a pea, maybe 1 gram, would hit with the energy of 200,000 tons of TNT. That's 15 times more powerful than the Hiroshima bomb. 1 pebble destroys your entire spacecraft in a fraction of a second. Even individual hydrogen atoms become a form of radiation. At 99.9% light speed, a hydrogen atom hitting your hull has the kinetic energy of about 7 billion electron volts. That's high-energy cosmic ray levels. Your spacecraft is essentially flying through a particle accelerator beam, with millions of impacts per second, each one depositing energy, creating secondary radiation, gradually degrading your shielding. How do you protect against this? Armor. Heavy armor would help against small particles, but armor is massive. Every ton of armor requires more energy to accelerate, more energy to decelerate. And armor thick enough to stop pea-sized particles at these speeds would need to be meters thick, made of the densest materials possible. We're talking about armor that might mass thousands of tons, and that armor would still gradually erode from the constant bombardment of atomic nuclei. Over years or decades of travel, your shielding would degrade, becoming thinner, less effective. Eventually, particles would penetrate, damaging systems, irradiating the crew. Some scientists have proposed using magnetic fields to deflect charged particles. This works for individual atoms, since hydrogen atoms can be ionized and then deflected by strong magnetic fields. But it requires enormous amounts of energy to generate magnetic fields strong enough to deflect particles at these speeds. And it doesn't help against neutral particles like dust grains, which aren't affected by magnetic fields. Others have proposed using a sacrificial shield, a large, expendable mass of material at the front of the spacecraft that absorbs impacts and gradually erodes away. But at 99.9% light speed, this shield would need to be enormous, adding even more mass to accelerate. Some have suggested using lasers to vaporize incoming particles before they hit. But how do you detect a grain of sand coming at you at 99.9% light speed? At that speed, an object travels 300,000 kilometers per second. Even if you detected it at a distance of 10,000 kilometers, you'd have 0.03 seconds to target it, fire your laser, and vaporize it completely. And space is three-dimensional. Objects could come from any direction. You'd need thousands of laser systems covering every approach angle, all operating autonomously at speeds far faster than human reflexes. The brutal truth is that we have no good solution to the space debris problem at these speeds. Every proposed defense adds mass, requires energy, and has failure modes. And in space, a single failure is catastrophic. One pebble gets through, and your multi-trillion-dollar, multi-generational mission ends in a flash of light. This is why, even if we solved the energy problem, even if we could accelerate to near-light speed, traveling through interstellar space at these velocities might simply be too dangerous. The universe doesn't care about our ambitions. Physics is not optional. But let's keep going. Let's imagine we solve the debris problem too. We have perfect shielding that somehow doesn't add mass and doesn't require energy. We're traveling at 99.9% light speed, making good time from the crew's perspective. What other problems do we face? Space is flooded with radiation. Cosmic rays, high-energy particles accelerated by supernovas, black holes, and other violent cosmic events, constantly bombard everything in space. On Earth, we're protected by our atmosphere and magnetic field. In low Earth orbit, Astronauts on the ISS receive more radiation than people on the surface. But Earth's magnetic field still provides significant protection. In deep space, between stars, there's no such protection. You're exposed to the full fury of cosmic radiation, and at near light speeds, this radiation problem gets worse in several terrifying ways. First, there's the radiation from the particles you're running into. Remember those hydrogen atoms we talked about? At 99.9% light speed, each impact creates secondary radiation as the atom crashes into your shielding. Your spacecraft essentially becomes a particle collider, with millions of high-energy impacts per second creating showers of gamma rays, X-rays, and exotic particles. Then, there's something called the cosmic microwave background. This is the afterglow of the Big Bang, radiation that fills all of space uniformly. To a stationary observer, this radiation is extremely cold, only about 2.7 degrees above absolute zero. But due to something called the relativistic Doppler effect, if you're moving at near light speed, the radiation in front of you appears blue shifted to much higher energies. At 99.9% light speed, the cosmic microwave background in front of you appears blue shifted from microwave wavelengths up to X-ray and gamma-ray wavelengths. You're flying into a wall of high-energy radiation just from the background glow of the universe itself. Additionally, any starlight ahead of you also gets blue shifted to higher energies. The gentle visible light from distant stars becomes harsh ultraviolet, X-rays, and gamma rays from your perspective. The crew would need heavy radiation shielding, probably several meters of water or polyethylene, rich in hydrogen, which is good at absorbing radiation, or perhaps lead and other dense materials. But again, shielding is massive. Several meters of water surrounding your entire habitable volume could easily add thousands of tons to your spacecraft mass. And even with perfect shielding, some radiation gets through. Galactic cosmic rays include heavy nuclei traveling at near light speed themselves. When these hit your shielding, they create cascades of secondary radiation. Some will inevitably reach the crew. On a 63-year journey at 99.9% light speed, the crew would accumulate significant radiation exposure. Even with the best shielding, they'd face increased cancer risk, potential genetic damage, and other health issues. Some might develop cancers that kill them before journey's end. Others might survive, but face health problems that reduce their quality of life on arrival. This isn't speculation. We know from studying astronauts on the ISS and from studies of radiation workers that long-term exposure to elevated radiation levels causes measurable health impacts. And we're talking about much higher radiation levels, sustained for much longer periods. You could mitigate this somewhat with medical countermeasures. Drugs that help repair DNA damage. Regular medical screening to catch cancers early. Possibly even genetic engineering to make the crew more radiation resistant. Though, that opens up a whole other can of ethical worms. But there's a limit to what medicine can do. Radiation damage is cumulative. The more you're exposed to, the more damage accumulates in your cells. By the time you reach Kepler-452b after 63 years of travel, you've received a lifetime of radiation exposure. Your DNA is riddled with damage. Your cells' repair mechanisms are exhausted. You arrive at your destination aged, damaged, possibly sick, after spending the prime years of your life in a metal can, traveling through the hostile void of space. And for what? To set foot on a world you'll have at most a few years to explore before your radiation-damaged body gives out? This assumes you even survive the journey. Space is unforgiving. Any number of things could go wrong over 63 years. A critical system fails. A piece of debris gets through your defenses. A solar flare from a nearby star bathes your ship in lethal radiation. A crew member makes a fatal mistake. An epidemic breaks out in the closed environment of the spacecraft. On Earth, if something goes wrong, we can call for help. Rescue teams can reach most places within hours or days. In space, traveling to another star, you're completely alone. The nearest help is 1,400 light-years away. If something goes catastrophically wrong, you die. Period. No rescue. No second chances. Let's talk about what it would actually take to build a spacecraft capable of reaching even 10% of light speed. Never mind, 99.9%. This is where theory meets brutal reality, and where our dreams of interstellar travel crash against the unforgiving rocks of engineering. The most realistic propulsion concept we have for interstellar travel is something called nuclear pulse propulsion. Specifically, a design study called Project Daedalus, developed by the British Interplanetary Society in the 1970 seconds. Project Daedalus was designed as an unmanned probe to reach Barnard's star, 9 light-years away. In about 50 years, the spacecraft would use nuclear fusion, the same reaction that powers the sun, to create thrust. Specifically, it would detonate tiny pellets of deuterium and helium 3 inches rapid succession, about 250 explosions per second. With each explosion creating thrust, the spacecraft would essentially be riding a controlled stream of nuclear explosions, using them to push forward. It's a brilliant concept in theory. And unlike warp drives or wormholes, it's based on physics we understand and technology we could theoretically build. But the scale of Project Daedalus is staggering. The fuel tank alone would need to contain about 50,000 tons of fusion fuel, primarily deuterium and helium-3. For reference, the entire International Space Station masses about 450 tons. The fuel tank for Daedalus would mass more than 100 international space stations. And that's just the fuel. The engines, the structure to hold everything together, the payload compartment, all of that adds additional mass. The total spacecraft would mass around 54,000 tons, about 120 international space stations. Project Daedalus was designed to reach 12% of light speed. To reach Kepler-452b at that speed would take about 11,700 years. Still completely impractical for a human mission. To reach 50% light speed, which would get us there in 2,800 years, we'd need a significantly more powerful version of Daedalus. The fuel requirements scale badly with desired velocity. To go roughly 4 times faster, from 12% to 50% light speed, you need vastly more than 4 times the fuel because you're fighting the tyranny of the rocket equation. The Tsiolkovsky rocket equation tells us that the change in velocity is proportional to the natural logarithm of the ratio of initial mass to final mass. This means that to achieve higher speeds, you need exponentially more fuel. To go twice as fast, you might need 5 or 10 times as much fuel. To go 4 times as fast, you might need 50 or 100 times as much fuel. A spacecraft capable of reaching 50% light speed might need millions of tons of fuel. The engineering challenges of building something that large in space are mind-boggling. You'd need to mine asteroids for raw materials. You'd need massive orbital shipyards. You'd need thousands of workers in space, supporting infrastructure, life support, power generation. You'd essentially need to build an industrial civilization in space before you could even start building your interstellar spacecraft. And we haven't even talked about the human payload yet. Because if this is a human mission, you need a complete, self-sustaining habitat that can keep people alive for thousands of years. Let's think about what a generation ship would need. First, you need living space. Humans are not good at living in cramped quarters for long periods. We need space to move, to exercise, to have privacy. Submarines, which have some of the most cramped living conditions in the modern world, allow about 70 to 150 cubic meters per person. Let's say we want better conditions than a submarine, so we allocate 200 cubic meters per person. For a crew of 1,000 people, which is probably the minimum for genetic diversity over many generations, that's 200,000 cubic meters of living space. If we arrange this as a cylinder 100 meters in diameter, it would need to be 25.5 meters long just for the living quarters. And we haven't added storage, engines, fuel tanks, agricultural areas, or any other facilities. You need food production. 1,000 people need to eat. On Earth, we get our food from farms, which ultimately get their energy from the sun through photosynthesis. On a spacecraft, you need artificial lighting for your crops, which requires energy. Or you could try meat production. But animals are inefficient at converting feed to meat. You're probably looking at a mostly vegetarian diet with protein from insects or vat-grown meat. You need water recycling. Humans need about 2 to 3 liters of drinking water per day, plus more for cooking and hygiene. For 1,000 people, that's 2,000 to 3,000 liters per day, or about 730,000 to 1,100,000 liters per year. You can't carry enough water for a 1,000-year journey. So you need perfect recycling. Every drop of water, including water in sweat, urine, and feces, must be recovered and purified. Any loss at all, even a tiny percentage per year, eventually leaves you with no water. The same is true for air. You need to maintain oxygen levels and remove carbon dioxide. Plants can help with this through photosynthesis, but you need a carefully balanced ecosystem. Too few plants, and CO2 builds up. Too many, and you waste resources. And ecosystems can collapse in unexpected ways. Biosphere 2, an experimental closed ecosystem built in Arizona in the early 1990 seconds, tried to create a self-sustaining environment for humans. It failed. Oxygen levels dropped unexpectedly due to microbes in the soil consuming more oxygen than anticipated. The team had to pump in oxygen from outside to keep the human crew alive. And that was with the Earth right there as a backup, with the ability to intervene and fix problems. On a generation ship traveling to Kepler-452b, there is no backup. There is no pumping in oxygen from outside. If your ecosystem collapses, everyone dies. Slowly, probably, as oxygen drops and CO2 builds up, but dies nonetheless. You need genetic diversity to avoid inbreeding. Population geneticists suggest you need a minimum population of about 500 people to maintain genetic health over many generations, though 1,000 to 2,000 would be safer. You'd also want frozen embryos or gametes to increase genetic diversity further. You need social structures that can maintain stability over dozens or hundreds of generations. You need education systems to pass on knowledge. You need government and laws to resolve disputes. You need culture, art, entertainment to keep people psychologically healthy. You need to maintain your technology. This is perhaps the most challenging aspect. The ship's systems, life support, engines, computers, all of this technology must continue functioning for thousands of years. Not just functioning, but able to be repaired when things break. Modern spacecraft are incredibly complex. The ISS requires regular maintenance and occasional replacement parts launched from Earth. A generation ship has no Earth to send spare parts. Everything must be manufactured on board or brought along. This means you need workshops, machine shops, 3D printers for making parts, stockpiles of raw materials for manufacturing, You need people trained to maintain every system, and you need to pass that knowledge down through generations. Think about that for a moment. The generation ship launches with engineers who designed and built the systems. They train the next generation. Those people train the next generation, and so on, for perhaps 50 or 100 generations until arrival. How do you prevent knowledge loss? Writing it down helps, but written manuals become outdated as systems are modified. They can be lost or damaged. Languages evolve over generations. Texts written in the language of the first generation might be difficult for generation 50 to understand. We have examples of this on Earth. The ancient library of Alexandria burned, and countless works were lost forever. Medieval monks copying manuscripts sometimes didn't understand the texts they were copying and introduced errors. Languages like Latin evolved into French, Spanish, Italian, Portuguese, and Romanian over many generations, such that modern speakers of these languages cannot understand classical Latin without special training. On a generation ship, you have the same risks of knowledge loss, but with far more catastrophic consequences. Lose the knowledge of how to maintain the fusion reactor, and the reactor fails. No power means no lights for food production, no water recycling, no air circulation. Everyone dies. You could try to preserve knowledge through digital storage, but digital storage has its own problems. File formats become obsolete. Storage media degrades over time. We have data stored on 1,960 seconds magnetic tapes and 1,980 seconds floppy disks that we can no longer read because we don't have the hardware to access them. And that's over just a few decades. Imagine trying to maintain digital archives over millennia. The most robust solution is probably redundancy. Multiple copies of all knowledge in multiple formats. Digital, printed books, oral traditions, apprenticeship systems where knowledge is passed directly from expert to student. But all of this requires resources, space, and people dedicated to preservation rather than other tasks. Now, let's talk about what might be the most difficult challenge of all: the human element. How do you maintain a society with a unified sense of purpose across hundreds of generations? The first generation, the people who board the ship, know what they're signing up for. They're volunteers, probably highly motivated, believing deeply in the mission. They're making a conscious choice to leave Earth forever, to spend their entire lives in space so that their distant descendants can reach Kepler-452b. That's admirable. That's heroic, in a way. But what about Generation 2? The children born on the ship never chose this. They were born into a life of confinement, living in a metal cylinder traveling through space. They never saw Earth. They never had a choice about their destiny. Do they feel the same connection to the mission? The same sense of purpose? Maybe. If their parents and the ship's culture emphasize the mission's importance, they might internalize that purpose. But they also might resent it. They might feel trapped, might wish they could have chosen a different life. And what about Generation 10, Generation 50, Generation 100? Earth becomes a myth to these people, a story told by elders, a place their ancestors came from thousands of years ago. Is it even real? How do they know? They've never seen it. They have no contact with it. For all they know, Earth might not even exist anymore. It's been thousands of years. For all they know, humanity went extinct centuries ago, and they're the only humans left in the universe. Kepler-452b is equally abstract. It's a destination they'll never see. Only their distant descendants will reach it. And those descendants are as unreal to them as their distant ancestors who left Earth. So what motivates them? Why should they maintain the ship? Why should they continue the journey? Some science fiction explores this concept with generation ships where later generations have forgotten they're on a ship, where the interior of the vessel has become their entire universe. They think the ship is the whole world. The mission is forgotten. Society collapses or transforms into something unrecognizable. Brian Aldiss's novel, Non-Stop, explored this idea, with a generation ship where society had collapsed into tribal warfare, with the inhabitants having no memory of their purpose or destination. In that story, the ship arrives at its destination, but the people aboard have long since forgotten why they're there. How do you prevent this? How do you maintain cultural continuity over timescales longer than recorded human history? You could try religious or ideological indoctrination. Make the mission a sacred duty. Instill it so deeply in the culture that questioning it is unthinkable. But this has its own problems. Religious fervor can lead to extremism, to persecution of those who question. It can ossify into dogma that prevents adaptation when circumstances change. You could try education, constantly reminding each generation of the mission's purpose and importance. But education requires resources and willing students. What if Generation 47 decides they're not interested in learning about the mission? What if they'd rather focus on art or philosophy, or just living their lives? You could try genetic or psychological engineering, creating people who are inherently more compliant, more focused on the mission. But this raises enormous ethical questions. Is it right to engineer humans to be mission-focused? Are you creating people or tools? And what happens when you reach Kepler-452b and need diverse, creative, adaptable people to colonize a new world? But you've spent generations selecting for obedience and focus. The brutal truth is that we don't know if it's possible to maintain a coherent society with a unified purpose over the timescales required for interstellar travel. We've never tried. We have no examples to learn from. We're guessing. And here's another dark possibility. What if the society on the ship fractures? What if factions emerge with different ideas about the mission? What if there's a civil war aboard the generation ship? On Earth, when societies fracture, people can leave. Dissatisfied citizens can emigrate. Different groups can occupy different territories. But on a generation ship, there's nowhere to go. You're trapped together in a confined space. If conflict emerges, it can't be resolved through separation. It has to be resolved through compromise, or through one faction dominating the other. And violence on a spacecraft is catastrophic. Damage to the hull, to life support, to critical systems could kill everyone. You can't have a war aboard a generation ship without risking total mission failure. So you need robust conflict resolution mechanisms. You need social structures that prevent conflicts from escalating. You need a culture that values compromise and cooperation above individual or factional interests. Can you maintain such a culture over thousands of years? Again, we don't know. It's an experiment we've never run. And there's one more horrifying possibility we need to consider. What if the ship's population evolves to the point where they're no longer compatible with the mission? Humans are evolved for life on Earth. 1G. Gravity. An oxygen-nitrogen atmosphere. Temperature ranges. We can survive. But on a generation ship, selection pressures are different. The ship probably has artificial gravity generated by rotation, but it might not be exactly 1G. The atmosphere is artificial, carefully controlled. The environment is completely different from Earth. Over many generations, people adapted to this environment might become less adapted to Earth-like conditions. They might lose bone density if the ship's gravity is lower than 1G. Their immune systems might become hypersensitive due to the sterile spacecraft environment, making them vulnerable to diseases on a planet with a real biosphere. They might become psychologically unable to cope with open spaces, after generations of living in confined quarters. By the time you reach Kepler-452b, your descendants might be so adapted to life on the ship that they can't successfully colonize the planet. They might arrive, look at this beautiful habitable world, and realize they can't live there. They've become a spacefaring species, adapted to artificial environments, unable to return to a planetary surface. The ship becomes their permanent home. Kepler-452b becomes just another view out the window. The mission fails, not because of technology or physics, but because the very people the mission was designed to serve evolved beyond its original purpose. Let's talk about money. Because even if we solved every technical problem, even if we figured out the physics and the engineering and the social challenges, we'd still face an economic barrier so enormous that it makes everything else seem trivial. Sending humans to Kepler-452b would be, without exaggeration, the single most expensive thing humanity has ever attempted. And I don't mean expensive like, we need to raise taxes, or we need international cooperation. I mean expensive, like we need to restructure the entire global economy for centuries. Let's try to put a price tag on this impossible dream. The Apollo program, which landed humans on the moon, cost about $25.8 billion in 1973 dollars, which is roughly $280 billion in 2024 dollars. This was the most expensive space program ever undertaken at the time, consuming about 4% of the US federal budget at its peak. The International Space Station has cost approximately $150 billion over its lifetime, funded by multiple nations over decades. These are staggering sums, representing decades of work by thousands of people, using cutting-edge technology. And they got us to the moon, just 3 days away, and into low Earth orbit, about 400 kilometers up. Kepler-452b is not 3 days away. It's 14,000 years away at 10% light speed, which is itself an impossibly ambitious speed that would require technology far beyond what we used for Apollo or the ISS. How do we even begin to calculate the cost? Let's try to be systematic about this. First, research and development. We need to develop propulsion technology capable of reaching a significant fraction of light speed. This isn't tweaking existing rockets. This is fundamental breakthroughs in physics and engineering. Nuclear pulse propulsion, if that's our choice, requires mastering controlled fusion reactions, something we've been trying to do for energy generation on Earth for 70 years without success. Let's be optimistic and say we could develop this technology with 50 years of intensive research and a budget of $1 trillion. That's about 7 times what we spent on Apollo, sustained over 50 years. It's probably a gross underestimate, but let's use it. Next, building the infrastructure. We can't build an interstellar spacecraft on Earth and launch it. It's far too massive. We need to build it in space, which means we need orbital shipyards, mining operations on asteroids or the moon, refining facilities, manufacturing plants, all in space. We need to establish a spacefaring industrial economy. This is a multi-generational project in itself. We're talking about launching millions of tons of equipment into space, or mining and refining raw materials in space. The ISS cost $150 billion and masses 450 tons. We need industrial facilities that might collectively mass hundreds of thousands or millions of tons. Let's say this takes 100 years and costs $10 trillion. Again, probably a massive underestimate, but let's use it. Then we need to build the actual spacecraft. Millions of tons of structure, engines, fuel, life support, habitats, food production facilities, backup systems, and so on. How much does this cost? There's no good comparison. We've never built anything remotely like this. But let's try scaling from existing projects. The ISS cost about $333 million per ton. If our generation ship masses 1 million tons, at ISS prices, that would be $333 trillion. But economies of scale might reduce the per ton cost. Let's say we get it down to $10 million per ton through advanced manufacturing techniques. That's still $10 trillion for a 1 million ton ship. So far we're at $1 trillion for R&D, $10 trillion for infrastructure, $10 trillion for the ship itself. That's $21 trillion total, roughly equivalent to the current US GDP. That seems almost manageable for a global effort sustained over centuries, right? But we haven't talked about the fuel yet. If we're using nuclear pulse propulsion, we need deuterium and helium-3. Deuterium is relatively common. It's an isotope of hydrogen that makes up about 0.015% of water. We have plenty of it. But helium-3 is rare on Earth. There's some in the lunar regolith, deposited by the solar wind over billions of years. We'd need to mine the moon for it, scooping up and processing millions of tons of lunar dust to extract tons of helium-3. The cost of mining helium-3 on the moon is hard to estimate since we've never done it, but let's say $100 billion to establish mining operations and another $100 million per ton of helium-3. If we need 25,000 tons, half of Project Daedalus's 50,000 tons. If we're going to a closer destination, that's $2.5 trillion just for the fuel. Actually, wait, we need to get to Kepler-452b, not Barnard's star. Kepler-452b is 237 times farther than Barnard's star, 1,400 light-years versus 5.9 light-years. We need much more fuel. Let's conservatively say we need 100 times more fuel. That's $250 trillion for fuel alone. Now our total is $281 trillion. For reference, the total wealth of all humans on Earth, every asset owned by every person and every government and every corporation, is estimated at about $460 trillion. We'd need to spend more than half of all human wealth to build one generation ship to Kepler-452b, and that's with wildly optimistic cost estimates and assuming no cost overruns, no failures, no setbacks. In reality, costs would almost certainly be much higher. Space projects routinely run over budget. The James Webb Space Telescope, originally budgeted at $500 million, ended up costing about $10 billion. That's 20 times over budget. If our generation ship costs 20 times our estimate, we're looking at $5,620 trillion, more than 10 times all human wealth. And even if we could afford it, even if every nation on Earth agreed to pool resources for centuries to build this ship, what's the return on investment? With conventional space missions, there's at least a plausible economic justification. Mining asteroids for platinum and rare earth elements could be profitable. Space-based solar power could provide clean energy. Space tourism could be an industry. Scientific research in microgravity has applications on Earth, but an interstellar mission to Kepler-452b? There's no economic return. The travel time is too long for resource extraction to be profitable. You can't mine Kepler-452b and ship resources back to Earth. The journey takes thousands of years. You can't establish trade. A round-trip communication takes 2,800 years. The only possible justification is survival. If Earth were facing imminent extinction, if a gamma-ray burst, or asteroid impact, or some other catastrophe threatened to end all life on Earth, then spending everything we have to establish a colony on Kepler-452b might make sense. It would be humanity's backup plan, a seed population to ensure the species survives. But even then, the economics are questionable. For $281 trillion, you could probably address almost any Earth-based extinction threat. You could build orbital defenses to deflect asteroids. You could develop technologies to survive climate change. You could build underground bunkers to survive nuclear war. You could establish self-sufficient colonies on the Moon or Mars, which are infinitely easier to reach than Kepler-452b. The only scenario where Kepler-452b makes economic sense is if Earth becomes completely uninhabitable. The Moon and Mars are also unsuitable, and we have centuries of advance warning, so we can build the ship. That's a very specific and unlikely scenario. For any realistic future we can foresee, the economics of an interstellar mission to Kepler-452b simply don't work. It's not just expensive, it's ruinously, civilization-threateningly expensive for no tangible benefit. Here's where things get philosophically interesting and even more depressing. Suppose we solve all the problems. We develop the technology. We find the money. We build the ship. We recruit the crew. We're ready to launch. Should we? This is known as the weight calculation, and it's a genuine dilemma in interstellar mission planning. The problem is this: technology improves over time. If we launch a generation ship today with current technology, traveling at 10% light speed, it will take 14,000 years to reach Kepler-452b. But if we wait 500 years and develop better propulsion technology that can reach 50% light speed, a ship launched then would take only 2,800 years and would arrive 11,200 years before our current ship. Our first ship, launched with great fanfare and enormous sacrifice, arrives at Kepler-452b to find that humanity is already there, having arrived thousands of years earlier on a faster ship launched much later. The first crew sacrificed everything, spent their entire lives and the lives of dozens of generations traveling through space, only to arrive at a destination that's already been claimed by their own species. They're not pioneers. They're not heroes. They're obsolete. This is the cruel logic of exponential technological growth. If technology continues to improve, launching an interstellar mission at any given time risks having that mission overtaken by future missions with better technology. So when do you launch? How do you know that technology has advanced enough that launching now makes sense? You don't. You can't. There's always the possibility that waiting another century will yield better propulsion, better life support, better everything. Some theorists suggest that you only launch when technology reaches a plateau, when the rate of improvement slows to the point where waiting no longer yields significant advantages. But when is that? And how do you know you've reached that point and not just a temporary slowdown? For Kepler-452b, 1,400 light-years away, the weight calculation is brutal. Any propulsion technology we could realistically develop in the next century would be so slow that a ship launched in the next 500 years would almost certainly overtake it. So the rational decision is to wait. But wait how long? Until when? What's the threshold? There's no clear answer. And in the meantime, we don't go anywhere. We're trapped in analysis paralysis, unable to commit to a mission because we know it will probably be a waste of resources. Here's an even darker thought. What if technology never advances enough? What if the laws of physics really do impose hard limits on propulsion, and we never develop anything significantly faster than nuclear pulse propulsion? Then waiting is pointless. We should launch as soon as we can, but we won't know if we're at the limit of possible technology until we've exhausted every possible avenue of research. And that could take centuries or millennia. Do we wait that long? Do we launch earlier and risk being overtaken? It's a paradox with no good solution. And it suggests that for destinations as distant as Kepler-452b, we might be stuck in a permanent state of not yet, always waiting for better technology that might never come. Throughout this video, I've been assuming we're sending humans to Kepler-452b. Living, breathing, biological humans who need air and food and water, and don't age well. What if we don't? What if we send machines instead? Robotic probes don't need life support. They don't need food or water. They don't care about radiation, at least not as much. They can be built much smaller and lighter than a human-carrying spacecraft. They can potentially be accelerated to higher speeds. The Breakthrough Starshot initiative, which I mentioned earlier, proposes sending tiny spacecraft, essentially computer chips with light sails, to Alpha Centauri. These would be accelerated by powerful ground-based lasers to about 20% the speed of light. At 20% light speed, a probe would reach Kepler-452b in about 7,000 years. Still a very long time, but at least the probe doesn't care. It doesn't get bored. It doesn't question its purpose. It just travels. When it arrives, it takes pictures, analyzes the atmosphere, sends data back. Another 1,400 years later, we receive the data. Total time from launch to receiving results, 8,400 years. That's not too bad in cosmic terms. If humans launch such a probe today, in the year 2025, we'd receive the first images of Kepler-452b in the year 10,425 CE. What will human civilization look like then? Will we even still exist? Will anyone remember that we launched this probe? But at least it's possible. Unlike a human mission, which might never happen, a robotic probe mission to Kepler-452b could actually be launched with foreseeable technology. What if we send digital humans, upload human consciousness into computers, and send those? This is pure speculation at this point. We don't know if consciousness can be uploaded. We don't understand consciousness well enough to even know if it's the kind of thing that could be digitized. But let's assume it's possible. A digital human doesn't need air or food. They could be put into a kind of hibernation during the journey, experiencing subjective moments while thousands of years pass objectively. They could arrive at Kepler-452b, download into robotic bodies or cloned biological bodies, and explore the planet. This solves many problems. No life support, no generational continuity issues, smaller spacecraft. But it creates new questions. Is a digital copy of a person still that person? If we upload someone and then launch their digital copy to Kepler-452b, has that person gone to Kepler-452b, or have we just sent a copy while the original remains on Earth? If the original person dies, does that matter? Is the copy a continuation of their existence or a separate entity? These are deep philosophical questions without clear answers. And that's assuming consciousness upload is even possible, which is far from certain. What about generation ships with frozen embryos instead of live crew? Launch a ship with frozen embryos and artificial wombs. When the ship arrives at Kepler-452b, the onboard AI systems thaw embryos, grow them to maturity, and raise them. The first generation of humans at Kepler-452b never lived on Earth. They're raised by machines to colonize a new world. This is ethically troubling. We'd be creating humans who never had a choice about their existence, raised by AI without human parents, tasked with colonizing an alien world. What kind of psychological damage might that cause? Is it ethical to create people this way? But it might be the only way to establish a human presence on a world as distant as Kepler-452b. No generational continuity problems. No need for a massive habitat to support humans during the journey. just frozen genetic material and the systems to bring it to life on arrival. Each of these alternative approaches solves some problems while creating new ones, and none of them give us what we really want. The ability for living humans to travel to Kepler-452b and back, to explore the planet firsthand, to meet whatever life might exist there. At best, we can send our robots, our digital ghosts, or our genetic legacy, but we ourselves cannot go. Number, what if there's life there? 3 hours to 3 hours, 15 minutes. Let's talk about the possibility that haunts every discussion of Kepler-452b. What if there's life there? What if there's intelligent life? What if there's a civilization looking back at us right now? We have no evidence of life on Kepler-452b. We've detected no radio signals, no obvious signs of technology, no clear biosignatures in the atmosphere. But our ability to detect such things is limited. We might simply not be looking in the right way or with sufficient sensitivity. Kepler-452b is older than Earth. If life emerged there and followed a similar trajectory to Earth, they could be far more advanced than us. They might have developed spaceflight millions of years ago. They might have already spread across their solar system, or even to nearby stars. Or they might be exactly at our level of development. Or they might be pre-industrial. Or they might be single-celled organisms in their oceans, following an evolutionary path similar to Earth's, but at a different point along that path. Or there might be no life at all. The planet might be sterile, either never developing life or having lost it to some catastrophe. We don't know. And here's the painful truth. Even if there is life on Kepler-452b, even if there's a thriving civilization, we can't meaningfully interact with them. Radio communication travels at the speed of light. A message from Earth to Kepler-452b takes 1,400 years. A reply takes another 1,400 years. A simple hello and hello back takes 2,800 years. By the time they receive our message, human civilization could have collapsed. By the time we receive their reply, we might not even exist anymore. You can't have a conversation across 1,400 light years. You can't have diplomacy. You can't have trade. You can't even really have communication in any meaningful sense. You could send them our encyclopedia of knowledge. They receive it 1,400 years later. They send back their encyclopedia. We receive it 2,800 years after we sent our first message. By then, everything in our encyclopedia is outdated, ancient history, and everything in theirs describes a civilization 1,400 years in their past. We'd be exchanging messages with ghosts. Every transmission is a time capsule from the distant past. By the time anyone receives anything, the sender might be long dead, their civilization transformed beyond recognition or extinct. And we certainly can't visit them. All the problems we've discussed apply. The distance, the speed limit, the engineering challenges, the economic costs. If we can't send humans to Kepler-452b, we can't send humans to meet any civilization that might exist there. So, even if we confirm that Kepler-452b has intelligent life, even if we detect their radio signals or see city lights on their night side, we're stuck looking at them from 1,400 light years away, unable to reach them, unable to communicate in any meaningful way. We'd be like two prisoners in adjacent cells, able to see each other, able to shout to each other, but unable to touch, unable to truly interact, forever separated by the vast gulf of interstellar space. This is perhaps the cruelest aspect of Kepler-452b. Not just that we can never go there, but that even if there are people there, people who might be remarkably like us, who might share our curiosity about the universe and our desire to connect with other intelligent beings. We can never meet them. We can never shake their hands, never share a meal, never exchange ideas in real time. The universe is full of wonders, possibly full of life, perhaps teeming with civilizations, and we're all alone, trapped on our respective worlds, separated by distances so vast that meaningful contact is impossible. So what does all this mean? Why does it matter that we can't visit Kepler-452b? I think it matters because it tells us something profound about our place in the universe. For all of human history, we've been explorers. Every frontier was eventually crossed. Every ocean was eventually sailed. Every mountain was eventually climbed. When we ran out of frontiers on Earth, we looked up. We went to the moon. We sent probes to every planet in our solar system. We've landed on comets and asteroids. We've sent spacecraft beyond the edge of the solar system. Space was the final frontier, and we conquered it, or so we thought. But Kepler-452b shows us that space isn't a frontier. It's an ocean so vast that we can see other shores, other islands of possibility, but we can never reach them. The solar system is our island, and we might never leave it. This is a profound shift in how we think about humanity's future. The science fiction dream of spreading across the galaxy, of meeting alien civilizations, of establishing colonies on distant worlds, might be just that. Fiction. Reality might be much more constrained. We might be stuck in our solar system forever, able to colonize the moon and Mars, maybe establish habitats in the asteroid belt or on the moons of Jupiter and Saturn, but never able to reach another star. The universe is vast beyond comprehension. There might be billions of habitable planets in our galaxy alone, and we might only ever get to see one of them, Earth. That's a hard truth to accept. We're a species that's used to pushing boundaries, used to achieving the impossible. We split the atom. We decoded DNA. We put humans on the moon and rovers on Mars. We've accomplished things that would have seemed like magic to our ancestors. But the speed of light doesn't care about our ambitions. Physics doesn't bend to human will. The universe has rules, and we can't break them, no matter how clever we are or how much we want to. Kepler-452b represents the limits of human reach. It's a world we can see but never touch, a destination we can dream about but never achieve. And there are billions more like it, scattered across the galaxy, each one forever beyond our reach. This isn't a reason for despair, but it is a reason for perspective. We're not the masters of the universe. We're not even the masters of our galaxy. We're a species on a single planet, in a single solar system, with the ability to explore our immediate neighborhood, but not much beyond. And that's okay. That's not a failure. That's just reality. The universe doesn't owe us accessibility. The fact that we can see Kepler-452b doesn't mean we have a right to visit it. The fact that it exists, that it's out there, is itself a gift. It expands our understanding of what's possible. It tells us that Earth-like worlds are common, that the conditions for life might be widespread, that we're probably not alone in the universe, even if we never meet our neighbors. Kepler-452b teaches us humility. It reminds us that we're small, that our reach is limited, that some mysteries will remain unsolved, some questions unanswered, some frontiers uncrossed. And maybe that's important. Maybe we need to be reminded that we're not all-powerful, that we can't do everything, that the universe is bigger than us and always will be. So, if we can't visit Kepler-452b, what can we do? First, we can keep looking. The discovery of Kepler-452b was made possible by the Kepler Space Telescope, which stared at a single patch of sky for years, watching for the tiny dips in starlight that indicate a planet passing in front of its star. We have newer, more powerful telescopes now. The James Webb Space Telescope can analyze the atmospheres of some exoplanets, looking for chemical signatures that might indicate life. Future telescopes will be even more powerful. We might find habitable worlds much closer than Kepler-452b. The nearest star system, Alpha Centauri, is only 4.37 light-years away. We haven't found any Earth-like planets there yet, but we're still looking. Proxima Centauri, part of the Alpha Centauri system, has at least 2 planets, including one in the habitable zone, though it's probably tidally locked and might not be truly Earth-like. If we find a habitable world around Alpha Centauri, the conversation changes dramatically. A journey of 4.37 light-years is still enormous, still perhaps beyond our current capabilities, but at least conceivable. At 10% light speed, it's a 44-year journey. At 20% light speed, it's 22 years. Still difficult, still expensive, but within a single human lifetime, we can explore our own solar system. Mars is there, waiting. It's not as nice as Kepler-452b, not even close, but it's achievable. We could have humans on Mars within the next 20 years, if we committed to it. We could establish permanent settlements within 50 years. The moons of Jupiter and Saturn are fascinating worlds. Europa has an ocean beneath its ice that might harbor life. Titan has lakes and seas of liquid methane, a thick atmosphere, and complex organic chemistry. Enceladus shoots geysers of water into space from its subsurface ocean. These worlds aren't habitable by Earth standards, but they're scientifically invaluable. Exploring them could teach us about the origins of life, about the possibilities for life in environments very different from Earth, about how planetary systems form and evolve. We can build better telescopes and study Kepler-452b from here. We might be able to detect oxygen and methane in its atmosphere, which would be strong evidence of life. We might detect industrial pollutants like CFCs, which would be evidence of technological civilization. We might even be able to map its surface, identifying continents and oceans. We can send robotic probes to nearby stars, if not to Kepler-452b. The Breakthrough Starshot Initiative, if successful, could send tiny probes to Alpha Centauri within the next few decades. The probes would take about 20 years to get there and another 4.37 years to send back data, meaning we could receive the first close-up images of another star system by around 2070 or so. That's not nothing. That's remarkable. That's humanity reaching beyond our solar system for the first time. We can search for signals from other civilizations. SETI, the search for extraterrestrial intelligence, has been listening for radio signals from space for decades. We haven't found anything yet, but we're improving our techniques, listening to more frequencies, covering more of the sky. If there is a civilization on Kepler-452b, and if they're transmitting radio signals, we might detect them. We couldn't respond in any meaningful way, couldn't have a conversation, but we'd know we're not alone. That would change everything, even if we could never meet them. We can take care of our own planet. This is perhaps the most important point. We have one habitable world that we know of, Earth. We're damaging it through climate change, pollution, habitat destruction, and resource depletion. If Kepler-452b is forever out of reach, if we can never escape to another Earth, then this Earth is all we have. We need to protect it. We need to preserve its ecosystems, stabilize its climate, ensure it remains habitable for future generations. All the money and effort we might dream of spending on an impossible mission to Kepler-452b would be better spent making sure Earth remains a place worth living. That's not giving up on exploration. That's recognizing priorities. And who knows? Maybe in 1,000 years, or 10,000 years, if humanity survives and continues to advance, we'll develop technologies we can't even imagine today. maybe our distant descendants will find a way to reach Kepler-452b. Or if not Kepler-452b, some other distant world. Maybe they'll look back at us and marvel that we could only travel at a tiny fraction of light speed, the way we look back at medieval sailors who took months to cross an ocean we can now cross in hours. Maybe the universe will open up to them in ways we can't foresee. Or maybe they'll face the same limits we do, and they'll have to make peace with living in a single solar system, just as we do. Either way, that's not our problem to solve. That's for future generations, if they exist. Our job is to survive, to learn, to explore what we can reach, and to take care of the world we have. We've spent nearly 4 hours together, exploring why we can never visit Kepler-452b. We've talked about the distances involved, the speed of light barrier, the engineering nightmares, the economic impossibility, the social challenges, and the philosophical implications. I want to end on a note that's neither despair nor false hope, but something like acceptance. Kepler-452b is 1,400 light-years away. It's a world that might be the most Earth-like planet we've ever discovered. It might have oceans and continents. It might have life. Possibly even intelligent life. It's tantalizingly similar to Earth in almost every way we can measure, and we will never go there. Not in your lifetime. Not in your children's lifetime. Not in 1,000 lifetimes. The distance is too great. The physics are too unforgiving. The economics are too prohibitive. The engineering challenges are too severe. This is a hard truth, but it's a truth we need to accept. The universe is vast beyond human comprehension, and we are small. Some frontiers cannot be crossed. Some mysteries will remain unsolved. Some worlds will remain forever beyond our reach. But that doesn't make Kepler-452b less important or less valuable to know about. The fact that we discovered it, that we can study it, that we can learn from it even from 1,400 light-years away, is itself remarkable. Every time we discover a new exoplanet, every time we find another world that might harbor life, we're reminded that Earth isn't unique. The universe is full of worlds, possibly full of life, maybe even full of civilizations. We're part of something vast and ancient and magnificent. We can't visit those worlds, but we can appreciate them. We can study them. We can let them inspire us to take better care of our own world, because it's the only one we can reach. Kepler-452b is the forever unreachable Earth. It's a reminder of both the vast possibilities of the universe and the limits of human capability. It's beautiful and frustrating in equal measure. But maybe that's okay. Maybe we don't need to visit every world we discover. Maybe the point isn't to touch everything, to conquer every frontier, to plant flags on every distant shore. Maybe the point is to look, to wonder, to imagine. Maybe the point is to know that we're part of a universe so much larger and stranger and more wonderful than we can fully comprehend. Kepler-452b exists. It's real. It's out there right now, orbiting its ancient sun, perhaps bathed in sunset light that looks almost like our own, perhaps home to life forms we can never meet, perhaps even home to people who are having this exact same conversation about Earth, wondering if they'll ever be able to visit us. We can't reach them. They can't reach us. We're separated by an ocean of space and time, too vast to cross. But we're under the same laws of physics, made of the same matter, looking up at the same cosmos, asking the same questions. That connection, tenuous as it is, matters. We're not alone in the universe, even if we're alone in our reachable neighborhood. And that's something. So the next time you look up at the night sky, think about Kepler-452b. Think about that distant world, 1,400 light-years away, that we'll never visit. Think about the light from its star. Light that left during the time of the fall of Rome, that traveled across the vastness of space for 14 centuries, and finally reached your eyes tonight. You're seeing across time and space to a world you'll never touch. And in its own way, that's as beautiful as visiting would be. Maybe more so, because unreachable things have a beauty all their own. They remain perfect in our imagination, unmarred by the disappointing realities that often accompany actual exploration. Kepler-452b is forever unreachable, and maybe that's exactly what makes it so precious. Thank you for spending these 4 hours with me, exploring the mathematics of impossibility and the physics of heartbreak. Thank you for thinking about these deep questions, about our place in the universe, about the limits we face, and about what it means to be human in a cosmos that's so much larger than we are. If this video made you think, if it changed how you see our place in the universe, if it filled you with wonder or sadness or both, please consider liking and subscribing. Share your thoughts in the comments. Tell me, does knowing about worlds we can never reach make you sad? Does it fill you with wonder? Does it make you appreciate Earth more, knowing it's the only habitable world we can access? I'd love to hear your perspectives. Until next time, keep looking up. Keep asking questions. Keep wondering about the cosmos. We might not be able to reach the stars, but we can still appreciate them. And in a universe as vast and strange as ours, appreciation might be enough.